For those who don't know us, is a New York City-based startup that has a full-stack Clojure team, and we actually are hiring right now. So you have Matt and Jeremy there, and if you want to work remotely in a cool team, just talk to us. What we do is outfitting, so we're taking retailer products, combining them together, enhancing them, and to inspire their buyers, their consumers. And today we're going to be building a movie recommendation engine that takes an input, like imagine you're on a web page. So the web page is showing up this James Bond movie, and then we want to be able to say what suggestion we should give you. So this is, we're going to be building this in Clojure. The idea is have a starter kit where we can then, take this idea with movies and export it to another level. So we want something in Clojure that is fast, accurate, and time-savvy. And basically the first part would be to explain it, the design regarding the start kit, and then to showcase it. So first pass is getting movie data. So you're on a web page, you have no idea who the user is, and you have 1 million movies that are accessible, and you need 10 results. So what do you do? What's the process to take 1 million movies and give you 10 results? And then the second pass will be, we're going to be adding some user preference. And then the third pass would be adding some user ratings, all the users of a platform, let's say. So for the first pass, 1 million movies is a lot, and basically we want a robust content-based filtering architecture. And the idea would be like to be fast enough to get something live to the user. So basically the idea here would be interesting to rely on a reverse index search engine, like for example, taking a metadata movie. Let's say for some reason in this James Bond there's French and police inside description or title or tags, etc. Then this, instead of looking at the old database here, that's the reverse index, you have an index that the keys are the tokens or the terms that are included in the search, or implicit search in that case. And then this point out to all the documents that match this token, so it's really fast to retrieve. And then with the documents, you can also tell like how many times this token is in a document. So you get a basic TF-IDF function where the more times in a document you get this token, and the least time this token is in other documents gives you the highest score. And the whole advantage of this is that most of the calculations are done offline, and the matching can be live because of this reverse index. So it could be interesting to have a search engine here. And then user preferences. Well, it depends on how many data we get regarding the user. But as a first pass, as a first start, we could still rely on content-based filtering. This is just having more data to create a query. So instead of having one movie metadata, you could have history logs, past searches, preferred movies, and then this would build up in a query. And we still could be in a space of content-based filtering. But when we add up these ideas of having all the users' ratings, then we're talking about collaborative filtering. And one concept interesting is re-ranking. It's like instead of having the search engine give you top 10 results based on their matching and then ranking by the scores, you ask for top 100 results and you re-rank to top 10 results using a ML model, for example, So that's the strategy we would be using. And 2 months ago, I was working with Lucene in really in search relevant stuff. And the documentation, what I found online was always, or most of the time, pointing to Solr, which is using a past Lucene for token matching and ranking. Lucene, how many have used Lucene before? Yeah, that's a lot of folks, right? So it's really a good standard. Elasticsearch is based on Lucene too. So Solr has a standalone server, REST API, declarative syntax for most of the time, high-level queries, and this is allowing domain experts to be able to use that without, and still keeping all the concepts in their mind. So you don't, since it's pretty short, it's really less consistent than Clojure. And it's actually funny, I couldn't find anything more consistent than Clojure. So when you go back and look at other DSL and stuff like that, there's always a smile. But it's still really powerful and could be used by some, not some programmers, some domain experts to tweak the algorithms. And it has re-ranking facilities with the Learning to Rank plugin. And I think that was announced by Bloomberg in 2015. They were looking for a way to re-rank, well, I mean, to create a best top 10 results on their news search. And they had something like 2,000 parameters to build the algorithm, so there was too much. And then that's why they released that plugin. So with Solr, you get all this, right? You get your index, you get query parsers, all the ranking stuff, and then you could use LTR to re-rank with machine learning, and there's also other strategies to re-rank your queries. And even though I put it longer because it's more expensive, but since you're doing that on a really subset, you can trust, you could use top 1,000 maybe, but you can trust like in those, I would have a fair good top 10. So that's the strategy we would be using. And then it's time saving in the sense that, well, it's Solr is really already developed, robust, declarative. This is fast. But is it in Clojure? Not really, though. There's a REST API. But we released just this week Corona, which is a wrapper for Solr 8 that will let you do this re-ranking. In the community, there was Flex that was compatible with Solr 5, but in Solr 5 they were not. We didn't have the possibility to do the re-ranking stuff. So we're excited just to release this, and just to let you know, expect some breaking changes, and please try it out and report any bugs, or if you want to enhance it, you're really welcome. So Solr is used by Netflix, Instagram, DuckDuckGo, Bloomberg, Walmart, Salesforce, Apple, Dell, and we do now have a little part of Corona, of our stack that uses Corona, so we could say that's the first company. So if you want to, as I said, experiment with us, you know where to find it. And then we also released Corona Demo, which is a showcase of how to use Solr in Clojure. It's a small project, and it has this movie recommendation engine, StartKit. So the first pass, as I said, is basic content-based recommendations. So we have a movie data set. It's not 1 million movies in the demo that you can find. But you can call, if you're serious about this, you can call the TMDB API and get all the movies you want there. So here are the keys that you get, all the metadata that you can get from a movie. And then Solr has its own server, so you install the Solr server. And then in your Clojure project, you specify each core, which is each index. So TMDB is one. And then you can specify all the configuration there. So you start Solr not in Clojure, and then you can run Clojure and create your core and add up some schemas regarding your data, schema types, and then schema fields, which would be like something like overview, title, etc. And schema types could be something like this, right? So you have, it's really similar to what Lucene has, though it's a data structure. So you can have index analyzer and query analyzer. So for example, the index analyzer, you would have this stop word filter. So before tokenizing, you remove your stop word. You make sure like Y space phi would match to Y phi together, and Y phi with a dash, etc. So you have a lowercase filtering, and the Porter steamer is really cool. Like probably a lot of you have used this, but the fact is like it's declarative. You just declare that, and it's done. You can use it and choose on which field you're going to use this. And for that example, on the query side, you can add up synonyms. So yeah, so you could have a database of synonyms, and there's one open source you could use also to do that. So then you create your index, and you're ready to make a first query using Corona. So here we query the word bond, and it's in a special type where it copies all the content fields, so you don't need to specify in which field you're querying. And then you tell the keys you want back in the maps that you get back. So you get a couple of metadata information regarding the response, and then you find out like these movies. For example, I create Bond, and I get Bond movies in there. So you in the demo we use a couple of others queries. And it's growing, and we're still, the DSL is somehow not intuitive completely, so you need to find that, field query, boost function, etc. So and the boost function itself is not in Clojure yet. So we will see if we need to actually parse all this, if it's some work that is worth it or not to create this. There's a JSON, this is based on the main API, query API, but there's also Solr exposes a JSON-based query API. It looks a bit more like Elasticsearch, where you have more data, a real data structure to actually specify the query. So that could be interesting. And then, so the first pass would be using the built-in function called more like this. And so the way it works, like you configure, you say, I want to get, the more like this will get you back interesting terms, which are not all the fields, all the terms you have in for a specific document. It would want only to extract interesting terms, which has the highest TF-IDF score across all the fields, and with some configuration like saying minimal token frequency and the minimal document frequency. So the more you raise minimal token frequency, it would be a use case would be something like a text, or you have a massive amount, well, I mean, few paragraphs or more, where you don't want to actually get back one word, but probably a word that is repeated more than once, etc. So you need some parameters, you need some back and forth to actually build up a query that makes sense, and then create your own function and just expose it to the user. And then the boost here, MLT boost, says, well, use the TF-IDF score because it filters down to a minimal set of information, this, for example. So this is like a really small piece of all the tokens you would find in the James Bond movies. And with MLT boost true, then you say, all right, give me the TF-IDF score and boost with this. And then we could say, well, at the end, we can also control with a second boost, where we say, all right, genres is more important, and overview is, but let's say keywords, we tested and it's not reliable, so we have an implicit score of 1, etc. So now this influence also the score you get back. And you can see that actually Bond have the highest score there, which makes sense because it's not in almost every movie except for James Bond movies. But the thing that is interesting is that there's no Bond entitled, so it figured out from a text that is an overview of the movie. So that's pretty good. So like the downsides though is like you cannot control, for example, to make sure like the movies you are suggesting are from the same year or the same decade in the same some kind of range. So using this from the built-in more like this, you cannot boost according to any number, parameter, or value you would have in your indexed data set. So we need a second option if you want, say, for example, to consider past search queries. So the person typed Bond and actually went and opened this movie, but before we can see what he was trying to access, maybe he got bored, didn't find what he wanted, or maybe he was expecting a Bond movie with race in it. So this you can just pass this to the query that is generated. So instead of using the more like this, like behind the scene interesting terms, what you do is you use the handlers to extract those terms, and then you build a query, and you can add also like more like these. So you could say, I want also to consider past watch movies or rating, etc. So, and you would pull actually the metadata of it. So that's the second pass. That's the second strategy. Now, it's not beautiful there, and the challenge or the goal would be actually to have some interesting closure helpers that could answer more cases that are built in, and that shows you a great API. And now we're at the recommendation with collaborative filtering, and the goal is to re-rank the very top recommendations based on the predicted rating a user would give a movie if he had rated it after seeing it. This is guessed by the machine learning model. So we add up some data, right? We had some movie metadata, so we add up users and ratings, and we did find a way to actually match the IDs from MovieLens dataset to the TMDB dataset. So in the repo you can play with it, and it works. And next, what you do is actually what Solr expects is you can store your features there. So the feature is something that your model, ML model, will use to run the model, to train the model. So you need to, you have LTR namespace is a Corona namespace that we started that have facilities to actually do that. So the top three, we decide, as we need a feature to be numeric, a numeric value, we just decouple genres into Boolean. For example, genre, action, true, false, etc. So true, false is then 0, 1, and we can use that same strategy for these type of fields. And then we could use directly or normalizing them as the direct numeric fields, popularity, vote average, runtime revenue budget. And then into the same store, you could add up the user profile information that will be used to match a user that is using a search, and then other users that have the same profile, what they like. So this will also be grabbed in the model. And basically, it gives you back a data structure that is uploaded to Solr, and that tells Solr the queries you need to run internally to create the feature value. In that case, it's simply counting. It will give you back a number. So for the genres, this only one in the field field of, there's no multiple values of the same thing, so it will count action, it will see action only once. So we get 0 or 1, whether it is in or not. So that's a strategy. We could have used probably other strategies, like labeling from 0 to X number, the categories. And then with some manipulation, we create 2 data sets, with one of which is for the training, and the other would be to test. So for the for the training, and this will create a neural network file afterwards that we can use back. So the features are just numbers there, and we have 300 movie features that are just those numbers, and then 3 user features that are added. So that means that the first layer, so this is a single dimension array. So there's no, and there's not the sense of proximity. Like if you do image detection, you would have X, Y, for example, and so the pixel next to each other, it's important to keep the same order. So this order is important, and there's 2 dimensions, plus the channels for each colors. So RGB, that's 3 channels, so it creates more nodes. And in this context, we only want like 1 dimension. So the little gray square one is just the user information that I got in, and this is from the query, as opposed to those 300 that is actually from the index that is attached to each document. And then, so the strategy here, it's to expand in more nodes and then go back to a rating. So for, let's say we do a first iteration in training, it goes back to a 2.8 rating, and then there's back propagation, and we are going to change the weights. So the little links between the nodes you see, we're going to change those weights, and then it will do that again and again and again. As a default, we set it to 1,000, and this is the neural networks where each layer will tend to become specialized and find out under the scene some concepts regarding what certain types of features combined together makes a movie good. How do they relate to each other? And we don't really see it, but in the end, the rating will be improved. And then what you need to do simply is in the query, you add up this key, and you pull, I mean, from there, I didn't add all the slides, but from there, you actually upload back. You can test your networks. We are using Cortex in this, and we have an MXNet namespace that is almost ready. That does the same thing as Cortex does. So if you guys want to actually complete it, how many of you use MXNet? 1, 2, cool, 3. So if anybody wants to complete the work there, just take a shot. And so basically, and so we are at query time, so we pass in some external feature information. For example, the gender, the age, and the occupation of a person. So this is how we use re-ranking. Now, re-ranked documents here is 100. If you trust really your model, you can go up. If you don't, or if it's not necessarily reliable, or if you want to stay objective in the movie you're recommending, like for example, content-based filtering is good, and if it's well tweaked, then it makes sense to have similar movies down that are actually where there's no influence with collaborative filtering. You could have actually 2 rows if you wanted, like similar, and then you may also like, which is different, and consider more the user, because it's sometimes the results we got, and it's not over, like we're going to do some more tweaking, but the results we get is it's supposed to be good according to the score, but it's not necessarily linked semantically to the movie you're asking for. So this idea of having some roles or even some facets, like let's say action movies, you would like this, or other type of dimensions, like you can group together a couple of different concepts and then do your recommendation based on that. And the other models. So this is one possibility. We could try something even more crazy. We could say, well, let's pass in every word of the index in as feature, and let's find out how the model actually gets it, and if it can actually infer a rating based on the description of a movie, or tags. If you have tags, you could pass in tags and try this out. So yeah, to conclude, we use Clojure in this experiment more than if we would rely on REST API and then have Java dependencies to actually call some Solr handlers, etc. So relying on the REST API is pretty cool. Then Corona is actually using it a lot. So then it's even better. You have some Clojure function directly in the API, but the query DSL is still something like of its own, except if we decide to move to the JSON API completely. As for the speed, this was fast. The relevancy was okay. I was a bit. I found it hard to do the second pass, which is going out of a more like this handler and make our own and pass in some information. Like there's specific parsers. You have eDismax, Dismax, Lucene parsers, and then you have more specialized parsers. And for eDismax, well, it does a disjunction. So basically, if you have something that matches really good at one of the terms you're searching has a high score, it will take only that score and remove all the other terms and do it for everything else. So this is a strategy to actually get really different results that are not just averages, and to get a variety in your results, but at the same time, sometimes it felt frustrating that you don't get James Bond movie by looking for similar movies, because you add up, let's say, Fast or Car in your history, and then a lot of car movies are showing up. So this ability to actually tweak and play with the DSL is something that is not really easy to get. And there are some specific conferences. I think in 2018, last year it was in Montreal, but there was like specific talks on this DSL for specific parser and how to. So you need some knowledge to actually grow your queries there. And then, yeah, that's the learning curve. So what we need in a Corona demo repo now is more metrics. Find a way to somehow build some kind of pipeline to run your model, to design your models and experiment with it at the level of the architecture. Actually, we didn't do it, but it will soon. We're gonna improve what we have in there. So I wanted to thank, special thanks to Alexei Makudin, who is the main architect regarding the Learning to Rank Cortex ML namespace, and he was actually really helpful. And Jeremy Rains, that is here, is the VP Tech of Statix that decided to, first it was some kind of side project, but then he decided to actually integrate, invest some time in it, and decide we can maintain it, having a bit of it in production already. Sanel, that worked a lot on the server side of on our team to actually install Solr, etc. And we have some docs that are improved on the Corona repo, so you can follow it to install Solr. And then Arthur Caillot, which had prepared and it's almost done, almost connected, a version using MXNet. So yeah, I thank you very much for your attention. This was pretty fast. I didn't want to talk too much. As you can see, I'm a French Canadian speaker, so normally I speak more. So I was restraining myself. But if you have some questions, let's dive in. Thank you very much. Yep.
All right, this is not a rehearsed question, so good luck, buddy. For the incorporating other users or like users like this, is that something you get out of the bag or with some configuration, or do you have to bring a separate like user similarity model to the table?
No, it's all together in this area, and the machine learning figure out by itself. It's like it's a composition of the whole thing. So that's counterintuitive. I'm not sure if it's answering your question well, but you can combine them, and it doesn't. You can try it out. We tried it out, and we got a decent score. And it's actually taking that parameter. But you could also have spatial models that you combine. And in 2015, there was not the capacity to combine the re-ranking steps. So we have one, but I think now we do. So you could have a re-ranking strategy that is using some model, and then you could re-rank again using another. So that could be it.